So, hello and welcome to my presentation. In this presentation, I'm going to give rise to one particular consideration as captured completely by the question on the slide. To what extent do similarities between the finite difference and binomial numerical methods generalize over the types of option valuation problems to which they are applied? Now, there are phrases in this question that may be a bit unclear to you. The first of which being the option valuation problem. Well, this is the problem of determining a fair value for the option or for an option. Before defining this problem, we must know the option for which the problem of very fairly valuing it is solved. In this research, or in my research, I shall consider two types of options only. The first of which being the European put option, defined as a contract, which says at the prescribed time in the future, known as the expiration date, the holder of the option has the right to sell a prescribed asset, known as the underlying asset, for a prescribed amount, known as the exercise price. The American put option is, well, very similar to the European option, the only difference being the fact that exercise is permitted at any time during the lifetime of the American option. We shall assume a set underlying asset to be a stock following a geometric Brownian motion. And the motion I have written in differential and informal notation here on the slide, and I hope in this way you can get an intuitive feel of the motion. Now, this Brownian motion, in combination with some stochastic calculus and an appeal to arguments involving supply, demand, and no arbitrage, which by the way lie at the heart of what we deem fair, gives rise to the European put valuation problem and the American put valuation problem. The difference in the problems stem from the difference in the nature of the option. Now, the European put problem is not only the partial differential equation that you see here on the slide. There are also some boundary conditions involved, such as the value of the put at its time of expiry. And as a whole, the European put option can be transformed into the problem of solving the diffusion equation. In a very similar fashion, the American put valuation problem can be transformed into a linear complementarity problem. And by the way, for determining the American put valuation problem, we have looked for inspiration at the obstacle problem. And by the way, the diffusion equation may also come familiar to those keen on chemical theory. And I thought it was kind of interesting to note how problems solved in chemistry or physics can be of great utility in finance or economics. The solution function to the diffusion equation and the linear complementarity problem are functions depending on two parameters, and thus are functions that are defined on a plane. With finite difference methods, we basically limit the plane to a rectangle. We discretize this rectangle, we approximate each partial derivative involved in the transformed valuation problems by their respective finite difference approximations, and then approximate the solution functions iteratively. And as you may see on the slide, there are various kinds of finite difference methods. We shall only consider the implicit and explicit methods, and they give roughly the same result. So now let's turn to the binomial method. So the binomial method utilizes a binomial tree containing stock values at various time steps, and each combination of time step and stock value correspond to a node in this binomial tree. By knowing what the option values are at the time of expiration, we can determine the option values at earlier time steps in this tree, and also eventually the option value at time t equal to 0. Now, as the tree gets more dense by including more time steps, we see that the solution value is the solution to the put valuation problems, and so we can almost regard the binomial method as a finite difference method. It is for this reason that we seek for some kind of unification between the binomial method and the finite difference methods that we have considered in the previous slide. And this is exactly the motivation for the research inquiry. In order to seek for an extent of unification of the methods under consideration, I ran some numerical simulations under financial parameters that often correspond to reality. You could think hereby for usual values of the interest rate or the volatility of stock prices over time. Now, the rectangle over which we found the solution functions has been discretized with respect to the stock price axis to only 1 degree, which is also a very high degree of discretization, and with respect to the time axis in 3 different degrees of discretization. And the reason for doing this has to do with the fact that there's little research done under this setting, and so these findings may be of utility of those who find this avenue of research an interesting one. First of all, varying the time to expiry and keeping the stock value fixed, we observe a discrepancy of a very particular nature of the finite difference method from the binomial result for the European put problem. But for the American put problem, no such discrepancy can be observed. A similar pattern can be observed if we let the stock value vary and the time to expiry fixed. As discretization with respect to the time axis is the only thing that varies as alpha varies, because alpha is a measure of discretization of the whole grid, we accredit the found discrepancy to finite difference approximations with respect to the s-axis that is involved in finite difference method. But since this is fundamental to application of the finite difference method, we conclude that there is no satisfactory unification between the methods, but note that we are being very vague with the word satisfactory here. And also, to end this video, note the ramifications of this on financial practices.